Okay, here's our first projectile situation that we've got. Now, these questions, I just lumped them together because they use the same scenario. And basically, in both of these questions, we want to know how high does it go? How far does it go? How much time is it in the air? What's its time of flight? How fast is it going when it hits the ground, et cetera, et cetera. Okay. So this situation here is perfectly symmetric because our we have no change in height from start to finish. Okay. Now, so we've got some different routes we can go because of that. Okay. So let's actually start with the idea about the speed when it hits the ground. Because it's symmetric, what that means is when this thing hits the ground over here, it's going to be going exactly the same speed that it was when it launched. No more, no less. Okay. So gravity has had the same amount of time to work on the vertical component. So the vertical component of its velocity goes to 0. And then it comes back to the same vertical component it had previously. All right. The x component doesn't change at all. Now, if there were some height difference, then what we would have to do over here is we would have to take out and look at the square root of that x component plus whatever has happened with the y velocity. Okay. So we could work it out just like that. If we needed to know, well, in this case, if we needed to know the angle, we know in this case, because it's symmetric, we know that's 30 degrees. But if we didn't know, like, for example, it landed higher or lower, okay, like that, then we would have to use our tangent relationship. All right, so we would say that the tangent of theta is Vy over Vx, like so. Okay, so we can find that out that way. So like, if we're shooting off a cliff or we're shooting up on top of a cliff, whatever, we can nail that down that way. Okay. So let's dig into, how far this thing's going to go. Okay. So what we'll do here is we're going to start with finding out what the x and y components of the initial x and y components of velocity are going to be. Okay, so Vox is just going to be 10 times the cosine of 30 degrees, and that is 8.66 meters per second. And for y, it's going to be 10 times the sine of 30, and that is 5 meters per second. Okay, just like so. So what we could do is we could start then with, if we want to find the time of flight, let's start with Optimus Prime. Okay, so our delta y, v naught y, delta t, okay, and minus a half g delta t squared. And you could see there I used the projectile version of that. Okay, I substituted in like that. Now our delta y is going to be 0 since we're starting and landing at the same place. Okay, now when that happens, okay, look what's going to happen algebraically. Okay, algebraically, if I divide by delta t, I lose that term right there. Okay, so I'm going to be left with v naught y is equal to 1/2 g delta t. So my time of flight is really easy to get here. So I'm going to have 2 v naught y over g. Okay, so double check that. Yeah, it looks pretty good. So that's going to be 2 onto 5 divided by 9.81. Okay, and I put that into my calculator, and what we get for our time of flight is 1.1. Hang on, I gotta pause this for just a quick second. I had to double check that number. It's 1.02. Okay, 1.02 seconds. Now I was a bad engineer. I didn't put my units in here. This is meters per second squared. And so you can see my meters are going to cancel. Boom, boom. And I'm left with, that's meters per second. One of my seconds cancels. Boom. So I'm left with seconds, which is what I have right here. Okay, so there's my time of flight. Boom, just like that. Now, if I was firing up on top of a cliff, or I was firing down a cliff, whatever, okay, so then I would have a non-zero delta y. So let's pretend for just a second that maybe I was firing down a cliff, maybe it's 10 meters to the bottom of the cliff. Then all I'd put down here on this side is I'd put -10. Okay, and I could do it exactly the same way. I could solve for t, and then I'd get my time of flight from start to finish. Okay, so it's a really powerful way to do that for finding time of flight. Okay, that sort of thing. Now, if for some reason I only wanted to know how much time it took for it to reach the apex, then we could do this and then divide by 2, or we could do something different. Okay, so let me show you that. All right, if we wanted to find the time to get to the apex, and again, this will work whether you're shooting up onto a cliff or down from a cliff, whatever. Either way, it's going to work. It's very versatile. Okay, I'm going to use SAM. Okay, because SAM tells us that the V final is V initial plus A delta T. Okay, so what we could do is we could say, let's rearrange this. We're solving for delta T. Okay, so I've got V final minus V initial over A. Okay, and then what we would do is we're going to do this just for, okay, let me make a note here. We're just doing this for the Y component. Okay, and so our final velocity is 0 because it's the final Y velocity when we're at the apex of that thing. So we're going to have 0 minus, and now we use our initial vertical component, which is the 5. Okay, and we divide by -g, okay, which is 9.81. Okay, now be careful there. Remember, g is 9.81. A is -g, so A is -9.81. All right, there we go, just like that. And if we work that out, it turns out to be 0.5097, okay, whatever, which is half of what we had over here, okay, because it's symmetric. But again, you know, if you were shooting up on top of a cliff or shooting off of a cliff down, then you couldn't say that it was half of the total time of flight. That would be wrong. But what we've done over here, this kind of a result is going to work no matter what your situation is. Okay, so that's good. Now, let's get to finding the height. Okay, we've got time of flight. Oh, we didn't get range. We should do the range while we're here. Okay, and I'm just going to set this up for you. Okay, because we know the range is just going to be V0 x times your delta t. Okay, and so our range is going to be 8.66 times our time of flight, 1.02. Okay, and whatever that gets you, that's your range. Okay, just like that. Okay, so let's get that height worked out. Okay, now what we're going to do is, you know, down here we just dealt with the y component of the velocity. We're going to do the same thing to find the height, but instead of using SAM, we're going to look at Bumblebee. Okay, so with Bumblebee, V final squared, V initial squared plus 2a, and we'll say delta y. Just like that. And so we're looking for delta y. Let's do a little bit of algebra here. We're going to have V final squared minus V initial squared over 2a. Okay. Now again, this is for the y components. Okay. And so again, at the top, at the apex of the trajectory, the y component goes to 0. We still start off with what we had before. So 5 squared. Okay, and divided by 2a, but a is minus 9.81. Okay, just like this. And that gets us 1.27 meters. Okay, and looks like I've been really sloppy with this one with my units. I'm sorry about that. I worked so hard all last semester to get you guys to use units. Let's look here. So this is meters per second. So it means it becomes meters squared, seconds squared. And down here I've got meters per second squared. So both my second squared terms are going to cancel out. And I'm just going to be left with the 1 meter left over. Okay. There we go. Just like that. Okay. So, good. Okay, I think we got everything. We found the height, found the range, speed when it strikes the ground. We found the time of flight. I guess it didn't ask for that, but we found it anyway, which we would have needed. Okay, cool. There's our first projectile.